Thank you very much for inviting me to speak today. It's a real honor to be in such distinguished company. When I was doing my master's degree, my supervisor once told me that everything has been done before. So to whatever extent I fail to cite previous work or give credit for earlier insights into the issues I'm going to discuss, I apologize in advance. It's only appropriate on this 50th anniversary of the Society that we acknowledge that the importance, or at least suspected importance, of vitrification for the survival of cells during cooling has been recognized since the earliest use of cryoprotectants. Cells survive freezing with cryoprotectants by remaining in unfrozen pockets between ice crystals. Viewed from a compartmental perspective, the role of cryoprotectants during slow freezing is to increase the volume of solution that remains unfrozen during cooling until the solution, the unfrozen solution, and cells within it eventually pass below the glass transition temperature and survive freezing by vitrifying intracellularly. On a water cryoprotectant phase diagram, slow freezing looks something like this. The unfrozen compartment follows the melting point liquidus line down to a point called Tg prime, at which point the unfrozen fraction becomes a glass and the cells are vitrified. These days, the term vitrification is used to refer to a process of using a high enough concentration of cryoprotectant that the system remains, that the whole sample remains free of ice during the cooling process. And on a phase diagram, the concentration of solutes during vitrification remains unchanged during the whole cooling process. An important point about the phase diagram is that the melting point line technically only applies to an ice crystal of infinite size. If we consider the case of ice crystals that are very small, nanometer small, their equilibrium melting point actually decreases. And what that means is that if we consider the process of ice nucleating and forming in a pure solution, free of any contaminants, it's actually impossible for ice to form in this region, because as soon as a minimal size ice crystal nucleates, like say 1 nanometer in radius, if it tries to do that in this region, it's going to immediately melt. So consequently, this region of the phase diagram is metastable. And the only way ice can form in this metastable region of the phase diagram is through a process called heterogeneous nucleation, where impurity particles in the solution act as a template on which ice begins to form. Schematically, heterogeneous nucleation looks like this. You have your solution, and then you've got these impurity particles and surfaces in the solution on which ice nucleates and then grows. In the laboratory, heterogeneous nucleation looks like this. This is a substantial concentration of ethylene glycol that we've vitrified, or I should say attempted to vitrify. And you can see in the solution that there's a large number of ice balls in it. At the center of each ice ball is a location where heterogeneous nucleation occurred, and then ice grew around that nucleation center as cooling continued. Now, below the metastable zone, we have ice forming by a process that we've heard a lot about today called homogeneous nucleation. In this zone, ice can form in pure solution spontaneously. So ice can nucleate spontaneously in this zone, which is traditionally called the doubly unstable zone. And doubly unstable is not a pejorative term invented by cryobiologists to dissuade you from trying to vitrify in this region. It simply refers to the fact that this zone is unstable against both ice nucleation and ice growth. But for simplicity on my phase diagrams, for us at a talk, I'm just going to call this the unstable zone. And that's where homogeneous nucleation occurs. So conceptually, on a molecular scale, you've got your solution of randomly organized water molecules and solutes, and on a very localized scale, homogeneous nucleation occurs. And homogeneous nucleation involves just basically mostly rotational reorientation of water molecules next to each other with a minimum of diffusion. And what this means is that it is not really related to viscosity very much. It can occur, homogeneous nucleation can occur even at extremely high viscosities, and in fact, as we heard from Austin today, the rate of homogeneous nucleation tends to actually be highest, oddly enough, at around the glass transition temperature. In the laboratory, this is an example of extensive low-temperature nucleation. There are innumerable nucleation sites in this solution around which ice is growing, just turning the solution milky. So with this background, we can define three forms of vitrification in cryobiology. There's equilibrium vitrification, where you can cool and rewarm at any rate with a high enough concentration of cryoprotectant and never worry about ice formation. There's metastable vitrification, where you're navigating through the heterogeneous nucleating zone of the phase diagram. And then there's unstable vitrification, where you're having to deal with homogeneous nucleation. This is my word for it. I'm going to call this, for the purposes of this talk, unstable vitrification, because we're passing through the unstable zone of the phase diagram. And I should mention that the dividing line between the left edge of the phase diagram and this white part of the phase diagram, which is basically unvitrifiable, is determined by cooling rate. So at a particular cooling rate, there's going to be a threshold concentration of cryoprotectant, which is just barely going to be vitrifiable on cooling. And that would be the far left edge of the unstable part of the cooling regime for vitrification. Equilibrium vitrification was used a few years ago by Kelvin Brockbank and his group to cryopreserve heart valves. It was advantageous in that application because you could store and ship, or at least ship heart valves at a temperature, a dry ice temperature at minus 80 degrees and not have to worry about ice formation. Then we have metastable vitrification. The premier application paper for metastable vitrification was Rawl and Fay's work in 1985, where they successfully vitrified mouse embryos, cooling at, in one case, at only 20 degrees Celsius per minute. At slightly greater concentrations in the metastable zone, you can do tricks like this. This, of course, was the work of Fay and Austin Angel and others in 1984, where they showed that you could perfuse a rabbit kidney with a metastable concentration of vitrification solutes and structurally vitrify it. And at still higher metastable concentration, you can do tricks like this. This is 2 liters of the M22 vitrification solution that we now use for preserving tissue at 21st century medicine. And you can see the thermocouple probe in the middle of the solution there, showing that this solution is actually at a temperature of minus 124 degrees Celsius below the glass transition temperature. This entire solution volume is vitrified, fracture-free even, and I'm keeping it clear in room air by having the surface here coated with methanol so it isn't frosting up. And in case you think that this is just a physics demonstration, this is a real solution that can actually preserve tissue. Well, we've shown that we can load and unload this solution from rabbit kidneys and reproducibly recover rabbit kidneys from a temperature of minus 45 degrees with full recovery. We've shown in one case that we were able to recover a rabbit kidney after complete vitrification at a temperature of minus 130 degrees and still obtain long-term life support of an animal with that kidney as the animal's only kidney. Dr. Fay and his surgeons have also used M22 to achieve essentially perfect vitrification and viability preservation of human corneas and long-term transparency of the corneas in 2 different xenotransplant models after vitrification. Vitrification in the unstable zone is being used a lot these days for gamete preservation, such as Peter's work, which I'll be discussing in more detail. And as far back as 1938, and then recently in 2002 rediscovered by Isachenko. It was Basil Luyet who first did this in 1938, and then Isachenko rediscovered it, that you can apparently vitrify sperm with no cryoprotectant at all by cooling it and rewarming it at ridiculously fast rates. And this has been called kinetic vitrification. And Igor Katkov explained that it works because sperm have a very high polymer concentration intracellularly. So I think in terms of the physics of what's happening with so-called kinetic vitrification, it's actually best regarded as another example of unstable vitrification in that part of the phase diagram. So we've shown that we can cool systems through the metastable and unstable zones of the phase diagram. But what about rewarming them? How do we get back to laboratory temperatures again? Some years ago, several years ago, we did some DSC studies of ice growth rates and ice nucleation rates in our M22 vitrification solution. And what we found is that the ice growth rate is maximum approximately 10 degrees below our solution's melting point, which is minus 55 degrees, whereas the ice nucleation rate is actually maximum, as Austin was reporting earlier, for more dilute solutions. The ice nucleation rate is maximum at about the glass transition temperature, and in fact continues for some distance even below the glass transition temperature. And we believe for various reasons, including the time dependence of this process, that this is heterogeneous nucleation in our solution. And then what happens is that if you look at the literature where other people have studied growth versus nucleation in cryoprotectant solutions, you find that for more dilute solutions, these curves broaden and begin to overlap. So what you find for all these solutions, though, and what you always find, is that the temperature of maximum growth rate is always greater than the temperature of maximum nucleation rate. And it's because growth rate really is viscosity dependent, whereas nucleation rate is driven more thermodynamically and depends less on the viscosity of the solution. So when we're cooling a solution, we're only going to get ice formation in the overlap region of the growth and nucleation zones. So we can, that makes it relatively easy to vitrify solutions, but rewarming is a much more difficult problem. And the reason is that as we cool, we pass through this entire nucleation zone. And then as we rewarm, we pass through it yet again, potentially extensively nucleating our solution. And then finally, to get back home, we have to pass through the entire growth zone. And that creates the paradoxical phenomenon of growing ice during rewarming called devitrification. If we're rewarming in the metastable region of the phase diagram, and we have heterogeneously nucleated ice present, devitrification looks something like this in the laboratory. This is a relatively concentrated solution of ethylene glycol that we're rewarming from vitrification at a temperature of minus 90. And as we keep warming, you can see a whole bunch of discrete little ice balls forming in it. And those were previously heterogeneously nucleated ice particles that are now growing as we get into the less viscous, warmer temperature zone. So that's devitrification in the metastable zone of the phase diagram. If you do DSC studies of where devitrification occurs, you can actually plot the temperature at which devitrification occurs during rewarming, and you obtain this line called the TD line, or the temperature of devitrification. And what you find is that as the solute concentration gets lower, the temperature of devitrification gets very close to the glass transition temperature. For metastable systems, it's possible to outrun devitrification if you just warm fast enough, because the number of ice nuclei are limited, and there's a lot of ice growth that has to occur for a significant amount of ice to form in the solution. And if you warm fast enough, you can basically avoid problems with devitrification in the metastable zone. Well, what about the unstable zone? Suppose you've vitrified a relatively dilute solution. How can you rewarm that? it turns out that you've got a real problem with rewarming solutions in the unstable zone of the phase diagram. This is a DSC plot of a 35% propylene glycol solution during rewarming. And you can see that as you, almost immediately as you pass through the glass transition temperature, you've got WOMP, this gigantic freezing exotherm, which is devitrification. And if you warm faster, you can, in little increments, move the temperature at which this happens upward, which is why I drew the TD curve as a bit blurry on the phase diagram. But to move this all the way up to the close to the melting peak, you have to rewarm this solution at a ridiculously fast rate, like on the order of hundreds of thousands or even 1,000,000 degrees a minute to obliterate this devitrification event. So based on the physics of the situation, it appears unavoidable that you're going to devitrify systems that you vitrified in the unstable zone of the phase diagram, that they're just going to get knocked over as you rewarm. So that raises the big question, why does unstable vitrification work at all? Let's look at a particular example. This is work by Pierre Boutron, cryopreserving red blood cells back in 1987. And what he did is he cooled the red cells at various rates in 2 different concentrations of propylene glycol. And what he found is that at first survival drops off as the cooling rate got too fast, which is what you expect from two-factor theory. But then oddly, he found that as the cooling rate was increased further, survival recovered. And notice, though, that he was using a very fast warming rate of 5,000 degrees a minute, and he could not get this recovery unless he used this very fast warming rate. If you compare these survival curves against the ice-forming behavior of the solutions during cooling, what you see happening is that the survival of these cells picks up at almost exactly the point where the solutions begin to vitrify. So out on the left side here, the cells are surviving by the classical slow freezing paradigm. But survival out here is happening apparently because these cells are vitrifying, but only just barely vitrifying. And what's interesting about this is that at the time Boutron calculated the critical warming rate of 35% propylene glycol to be 10 million degrees a minute. He later revised that downward, but still nowhere near 5,000 degrees a minute. And certainly for 30% propylene glycol, no one has even bothered tried to measure or calculate the critical warming rate of that because it would be ridiculously high. So there's no doubt that these red cells were devitrifying extensively, basically devitrifying to equilibrium during the warming process intracellularly, and yet they are surviving. So then we have the question, how can total intracellular devitrification be survived? There's clues in a few papers by, first of all, by Louvier and Rasmussen back in 1967, and then Forsyth and McFarlane in 1986. And I learned last night that Austin Angel was doing similar work in 1968. And what these workers found is that at certain concentration ranges, the devitrification event was coincident with the solution becoming optically opaque, which is exactly what you'd expect. If a solution freezes, you expect to see ice in it. But amazingly, they found that at some other concentrations, calorimetric devitrification occurred, but this devitrification, this devitrified solution would remain optically transparent and not turn opaque until warmer temperatures were reached. And if they plotted these results on a phase diagram, what they found is that solutions that were just barely vitrifiable when you rewarm them would would exhibit delayed opacity. Long after the point they devitrified, they'd remain transparent and not become opaque until they went up there. And then at higher concentrations, you would recover the behavior you'd expect of the solutions becoming opaque immediately upon devitrification. And this was demonstrated for a whole bunch of different cryoprotectant solutes. It was shown for polyvinyl pyrrolidone, ethylene glycol, propylene glycol, glycerol, and I think even sucrose. So there's some universality of this phenomenon. So why does it happen? Imagine you have 3 different concentrations of a hypothetical cryoprotectant with properties similar to glycerol. And I've modeled 3 different samples here and pretend that these are of the same size approximately as a cell. So you've got a 30 micrometer scale down here. And I'm going to cool these solutions. First of all, we're going through minus 60 degrees Celsius, and the low concentration of CPA has undergone early high temperature nucleation. The solution is still relatively non-viscous, so there's time for ice growth to occur as we continue cooling, and the solution on the left becomes opaque. So basically, this is an unvitrifiable concentration off to the far left white side of the phase diagram. The 40% solution at minus 100 degrees Celsius begins to undergo extensive homogeneous nucleation that continues as cooling continues. And you've got a highly nucleated solution here at minus 120 degrees. And the 50% solution at this temperature has just begun to nucleate, so you have more sparse nucleation in this solution. Now we're going to begin warming back up. As we warm back up to warmer temperatures, ice growth begins to be possible. So we see that the extensively nucleated solution in the middle begins growing ice crystals. And at a still warmer temperature and longer time, the solution on the right begins growing ice crystals as well. However, the solution on the right is growing a smaller number of ice crystals because it didn't form as many nuclei. So as we continue warming, notice that the solution on the right becomes opaque during devitrification. And it becomes opaque because these ice crystals are larger than a wavelength of light, whereas this solution here in the middle is completely devitrified to equilibrium, but it remains transparent because these ice crystals are smaller still than a wavelength of light. So we continue rewarming, and then once we get to approximately minus 60 degrees in this hypothetical experiment, we're now entering the temperature regime where recrystallization can begin to occur. And recrystallization happens because the vapor pressure of small ice crystals is larger than the vapor pressure of water, leaving larger ice crystals. So therefore, once the viscosity becomes low enough, larger ice crystals grow at the expense of smaller ice crystals. So the smaller ice crystals begin shrinking and the larger ones begin growing, and you get recrystallization. And finally, even the center solution turns opaque. So the center solution turned opaque because of recrystallization, not because of devitrification. I was actually able to demonstrate this in the laboratory on the first try. These are 3 different concentrations of propylene glycol. This is hard to do at slow cooling rates, but I managed to do it. And you can see that this solution is pretty milky. It's because it's just barely vitrifiable. It's actually basically unvitrifiable. And this solution devitrified to an opaque state during rewarming. But this solution is completely devitrified, but it's semi-transparent. All you see is a sort of bluish opalescence here. And I learned from Austin last night that this is actually a dangerous experiment to do because when transparent devitrification occurs, it happens at such a low temperature, so close to glass transition temperature, that the solution is still extremely rigid, and the sudden formation of this amount of ice can actually explode the test tube and send glass flying everywhere. So next time I'll be sure I wear goggles when I do this, or a face mask or something. So what does this have to do with cell survival? There's a variety of papers I found, I haven't even included them all on here, that have showed that cells can survive intercellular ice formation if the intercellular ice crystals are small enough. And these were generally electron microscopy studies. This one found the ice crystals had to be smaller than 500 nanometers, this one smaller than 100 nanometers. And there was another one by Tsuneo Takahashi, who found the threshold was 300 nanometers for survival of intracellular ice crystals forming. And coincidentally, that is also the same size scale that makes solutions transparent. So we have this remarkable physical coincidence that the size of ice crystals that can be survived when they form intracellularly is about the same order of magnitude required for the ice to be transparent. It related to all of these observations are Secchi and Mazur's observation that the temperature and kinetics of oocyte opacification and death during warming after vitrification were more consistent with recrystallization of previously devitrified ice rather than devitrification itself. And basically, this happened because they're operating in this unstable regime of concentration so that they were devitrifying during rewarming, but if they rewarmed fast enough, they could outrun recrystallization. But if you don't rewarm fast enough, you're going to get recrystallization of this devitrified solution, and ice crystals will grow to a lethal size. They also observed that higher cooling rates during oocyte vitrification paradoxically gave lower survival rates unless the warming rate was extremely rapid. This is kind of counterintuitive to those of us who do vitrification in the metastable regime, but we can understand why this is. It's because if you, nucleation, even homogeneous nucleation, is partly a kinetic phenomenon. And if you cool too fast, you'll only sparsely nucleate your solution. And then when you rewarm, your devitrification is going to lead to larger ice crystals during the devitrification event because you don't have as many nuclei, and you're going to have to rewarm even faster to avoid growth of these to a lethal size during recrystallization. Then you'd have to rewarm that solution to avoid growth to a lethal size during recrystallization. So it appears a picture is emerging that a lot of vitrification that's being done these days in the unstable regime intrinsically involves devitrification and knocking the solution, or at least the unfrozen solution, over to the equilibrium melting point side of the phase diagram, and then you continue upward along the TM curve, and whether or not you survive depends on the speed at which you continue up this to see if you can avoid devitrification. And this raises all kinds of questions. Like, I think a really interesting line of experimentation would be to cool really rapidly, basically as fast as you can, and then sneak back up to some temperature and hold isothermally for a while at various temperatures to see how much nucleation you got at those temperatures, and then cool back down and then rewarm and see how survival changes depending on the extent of nucleation. Because if this understanding is correct, the more extensively nucleated you are while avoiding the nuclei growing, the better your survival should be. Just one final point I want to quickly make is that water activity is not equal to vitrification tendency. And I'm out of time. I could give some really dramatic examples of this, but you have to be cautious in interpreting the glass-forming behavior of the external solution to the glass-forming behavior of the intracellular environment. But I think that the data is pretty clear that in the experiments we're talking about, intracellular devitrification is occurring just as it's expected in the external solution. So in summary, metastable vitrification may be the only form of vitrification in which systems remain ice-free during the entire cooling and warming process. And if you do vitrification passing through the water-rich, homogeneous nucleation zone in the phase diagram, that appears to intrinsically involve extensive devitrification and intracellular ice formation during warming. But this quote-unquote unstable vitrification works because homogeneous nuclei are so numerous and the ice crystals so small that cells are not injured if recrystallization can be avoided. And this realization opens up new possibilities for designing protocols that minimize ice growth while achieving a high density of intracellular nucleation. And if I have time, and if Peter will let me, I'm going to quickly answer or attempt to answer 3 of the questions that came up on email while we were organizing the symposium. One was, compared to pure water, is the effect of solutes in enhancing vitrification primarily a matter of their increasing the viscosity of the solution? And I would say no, it's only part of the story. The increase in viscosity is a kinetic effect, but adding solutes also decreases the melting point and the homogeneous nucleation temperature, which are thermodynamic effects. And there's also some solute-specific effects on vitrification, such as how different stereoisomers of 2,3-butanediol, for example, can have different vitrification tendencies. How can one experimentally distinguish between a scenario where A, cells vitrify during cooling but form innocuous intracellular ice crystals during rewarming, versus B, cells that form a large amount of innocuous intracellular ice during cooling? And the answer is that I believe that a linear cooling rate, that at a linear cooling rate, B is impossible. The conditions for forming an extensively large number of intracellular nuclei permitting survival upon rewarming are antithetical to significant ice growth occurring on cooling. And finally, if the events of warming a vitrified sample are, and these are the events of rewarming a vitrified sample, we first revert from a vitrified to a fluid state, and you grow ice crystals, which is devitrification, you recrystallize the ice crystals, and then finally you melt. Then why is 2 called devitrification instead of 1? Because you would think that by symmetry, if you vitrify something, that the exact opposite process should be called devitrification. We were talking about this last night, and the use of devitrification to refer to ice crystallization during warming is very long and historical. It goes back to the early 20th century, and it's too late to change it. So even though it's confusing, it's just the way it is. And that's all I have to say. Thank you.
Thanks, Brian. See if we have time to get back to this question from now. I'd like to use my chairman's prerogative to ask a couple myself. One important distinction, I think, between the devitrification and recrystallization. In the devitrification, you're seeing the full effect, where you're getting out the full evolution of heat and liquid diffusion. Whereas recrystallization is probably almost infinitesimally small differences in enthalpy between small crystals and large. So at least in theory, you might be able to, well, in fact, that figure you showed where you're so calorimetrically that the heat was being evolved before it turned opaque, would sort of support that. You were getting the heat release because of the devitrification. They were still too small to exhibit by recrystallization. And there was no heat associated with recrystallization.
Yeah.
Would you agree with that?
Yeah, if I recall correctly, the heat associated with recrystallization is just a few percent of the heat associated with the devitrification event, and it just tends to sort of blur into the beginning of the melting peak because the recrystallization that occurs at precisely the point the solution becomes non-viscous enough to begin melting. So, yeah, it's hard to see in calorimetrically.
And one other brief question I have is, do you consider devitrification as something occurring at a single temperature? Recrystallization is not clearly occurring. It's a kinetic phenomenon. It's occurring over a range of temperatures. I don't know how long. We measured it down at occurring at minus 80 C.
Yes.
It occurs minus 80 C up to maybe minus 40 and increasing rates. Presumably, it would occur even lower gradation of the heat.
Yes.
Do you consider devitrification occurring over a range? Is it kinetic, or do you consider it sort of like a phase, almost like a phase temperature?
They are both viscosity dependent. It's just that recrystallization requires a much lower viscosity than devitrification does. So what you're seeing is that devitrification happens once you get into a certain range of viscosity, but it's still a very high viscosity at which it can begin occurring. But it does ultimately depend upon viscosity, just as ice recrystallization does. It's just sharper and sooner.
Except that you're getting a heat of fusion, which is a phase property, and that's what devitrification is. You go from a glass to a
yes,
which has phase aspects to it.
Yes, but I wouldn't say it's a phase transition, obviously, the crystallization of ice, but the devitrification temperature is not a thermodynamic temperature because if you warm faster and faster, you can actually move slightly the temperature it happens at to warmer temperatures because it's ultimately dependent upon time-dependent growth of ice, which depends on viscosity.
Growth rate would be.
Yes.
Kinetic.
Yeah.
Okay, questions?
I have two small questions.
Can you? I'm sorry?
I have two small questions.
Yeah,
One question is, did you do experiments to demonstrate that nucleation of ice crystals?
I think you better use the microphone.
It works now. I'm sorry. Did you do real experiments to demonstrate that additional nucleation at low temperatures help to survive?
I did not, but I can tell you, the only experiment I did in this work was the test tube photograph that I showed. Otherwise, I'm just reading papers. But I can tell you that in the Forsyth and McFarland paper that looked at opacity in devitrification in the 1980s, what they found is that they could take a solution that would normally turn opaque during devitrification, and if they held it isothermally at a low temperature where more nucleation would happen, it would then be transparent during warming. So physically, it's been showed that you could have smaller ice crystals during devitrification if you have more nucleation. That's been shown.
No, it is reasonable hypothesis. That's why I'm wondering, did you use it already? And second question, which I was a little bit confused. You said that homogeneous nucleation can happen in any viscosity. You try to say that it's independent on viscosity?
No, I'm saying that it takes an enormously large viscosity to finally arrest it. In fact, it can't actually be arrested until you are 15 or 20 degrees below the glass transition temperature. Only then does it calorimetrically stop.
It doesn't match my experiments which we did with pit steponkos, where we specifically measure nucleation rate in ethylene glycol using this kind of cooling to this temperature, create nucleation, go back to when they grow, measure kinetic growth. You can evaluate nucleation kinetics, and as soon as you get to the glass state, it gets arrested. So viscosity arrested.
Yeah. Well,
and your curve also shows this, by the way.
Patrick Mell's work agrees with my work, not yours, in that respect, that if you do experiments where you go down to some temperature, like say 5 degrees below the glass transition temperature, 10 degrees below the glass transition temperature, and you park there for a long time. Like in our case, our solution is so stable that to get nucleation at a temperature, we have to park there for an hour. So if you hold for an hour at minus 130 degrees, and then you warm back up to the temperature of maximum ice growth to allow the nucleated ice to grow, what you find is that there is still a temperature dependence on nucleation that's occurring even below the glass transition temperature.
Depends how you measure glass transition, but you're right, viscosity will arrest it.
Eventually, yeah. But it's amazingly high to stop it.
I'd like just a brief discussion of your early description of the approach to what you call the unstable zone in terms of the crystallized size. That's a Kelvin equation calculation, I suppose. And then, is it okay to do that in a solution where you're not, where you have a situation different from the vacuum around? It's like a Kelvin equation requiring that the environment of the crystal be a vacuum?
You're referring to my graph of the phase diagram of the melting point as a function of crystal radius? Yeah, I should say that all I did to make that graph was a very naive thing. I used the Gibbs-Thompson equation to calculate the melting point as a function of crystal radius for 0% solute concentration, and then I interpolated between Tm and Th all the rest of the way down. So that wasn't rigorous at all.
But the question he's asking is, when you talked, you said Kelvin equation, but it was Gibbs-Thompson equation, which is analogous.
I didn't say Kelvin equation. No. Yeah.
I mean, wasn't it Kelvin Lord Thompson or something?
Yeah, it's the same equation, it's just a different phase.
Any other questions?
Thank you.